Okay, thanks, Debanjan. So today's lecture will be about transport bounds, and will connect nicely to the discussion that Debanjan had yesterday and maybe today on Planckin. But before going into the bounds, I just wanted to say a few more things about systematics of the effective field theory. So we in the past few lectures, we derived this leading order effective action for the simplest case of diffusion. We also got the version with momentum conservation and Navier-Stokes. I'll focus on this one for simplicity. And several of you asked quite rightfully why we're dropping a bunch of terms. Why are we dropping them? And I'd like to be a little bit more careful with this today. The point is that in effective field theory, we don't have the right to set terms to zero. We don't have microscopic control. This is not a theory of at all scales. And so generically, there will be many infinite corrections to the effective field theory. And let's try to be a little bit more careful now and see what they do. So from this leading order action, we can already see how fields scale. So scaling of our leading order Gaussian action tells us, first of all, that frequency scales like q squared in this diffusive setting, right? You can just compare the two terms that have a phi a and a mu. They have either two gradients or one time derivative. And we can also see the scaling of fields themselves. So just set a quick way to do this is to action to scale like 1. And choose a term. Let's choose the term with two phi a's. Has two spatial derivatives. Okay, so this scales like 1 over frequency q to the d. We have two derivatives, q squared by a squared. Omega scales like q squared, so we're left with phi a squared over q to the d. Okay, so you learn that fluctuations of phi a scale like q to the d over 2. Okay, and mu r will scale like phi a. You can see from this last term, they appear in the exact same way. They both have the same number of gradients. So mu r also scales like phi a. Okay, so this tells you that the 2-point function this tells you many things, but in particular, the 2-point function we can check should go like q to the d, which let's say let me write it in time domain would be 1 over t to the d over 2. Okay, and this is indeed how a diffusive 2-point function decays in time. We obtained the diffusive Green's function yesterday. Here I wrote just its Fourier transforms, which are useful to have. Okay, this is how diffusion spreads in time. If you inject charge or heat somewhere, eventually it'll start spreading like a Gaussian, and the height decays polynomially. Okay, so we see that we could have guessed this just from scaling. So now we can talk about corrections. How big are corrections to all of this? And these corrections will be very important because they'll tell us when this effective field theory is even valid, right? These corrections better not be large. So what corrections to the EFT? Well, first we'll have higher derivative corrections. Okay, terms that look similar, maybe they're still even Gaussian, but just have more derivatives than the ones I wrote. Maybe extra time derivatives or 2 extra spatial derivatives. Let me still assume isotropy just for simplicity. And so those will scale like q squared. So q squared goes like 1 over t, so this would give 1 over t corrections at late times to observables. Okay, so for example, this observable here 2-point function of charge density, but basically any observable has some leading order decay, and it's going to have corrections like this due to hydroactive corrections to hydrodynamics. Okay. At late times, these corrections go away, and it's in this sense that they're irrelevant and that this EFT is useful. Okay, but they are there. That's one source of corrections. Another source is nonlinear corrections or fluctuation corrections. Which come just from, here I wrote a Gaussian action, but we could, of course, have nonlinear terms. We talked about a few examples of nonlinear terms yesterday. So the nonlinear terms could just have more powers of the fields, okay? The phi A field always has to come with a derivative, but the mu field doesn't. So the most important, the most relevant nonlinear term will come from extra powers of the mu field. So extra powers of the mu field, and we just found that the mu field scales like q to the d over 2. Okay, and these will lead to nonlinearities and to leading order to cubic vertices in the effective field volume. For example, we have this diffusion term, but we can also have a term with one extra power mu r. You can check that this is still KMS invariant. And this term is kind of inevitable. In fact, it just comes from the fact that diffusivity generically depends on filling or temperature. And so, in fact, we even know its coefficient. Its coefficient is just the derivative of the diffusivity with respect to the chemical potential. Okay, that's an example of a nonlinear term. And so this will lead to a cubic vertex in the effective field theory proportional to this term. Okay. This turns out to be the leading vertex, but of course there are many more. There's going to be higher order vertices and so on. So this cubic vertex does several things. One thing it does is that it will lead to nonlinear response. Okay, you will now activate a 3-point function of densities or currents. You could play with other operators, but let me just talk about densities proportional to this vertex. Okay. So, and again, nonlinear response can either be viewed as nonlinear correlation functions in equilibrium or nonlinear response to external probes. That's one thing it does. It will also lead to, it can feed back into linear response and lead to fluctuation corrections to linear response. A diagram like this. A thermal fluctuation, a loop in the effective field theory, which will give a correction to our, to just linear response, conductivities or our density 2-point function. So for this, you need 2 vertices, 2 d prime vertices. And so the correction will be of order q to the d over 2 times q to the d over 2, which goes like 1 over t to the d over 2. Okay, so a correction to any observable. Let me still focus on this simple density 2-point function. That looks like this. Okay, and in fact, we even know its coefficient in this case. I won't, roughly it's d prime squared. Okay, and these corrections are sometimes called hydrodynamic long time tails. So here we're really starting to see the predictive power of the effective field theory, right? Because, okay, true, it does have some coefficients that it doesn't predict, doesn't tell you what the diffusion constant is or its dependence on chemical potential, but it tells you that these things enter in many independent observables, right? So for example, a temperature or filling dependence of the diffusion constant is tied to nonlinear response and is also tied to intermediate time corrections or intermediate frequency corrections to transport. Nonlinear response, which you can measure in many different ways, but for example, a three-point function, and also tied to corrections to linear response. Okay, so with all this, we now can find the general structure of corrections to transport at late times or low frequency. Let me illustrate it with still this density two-point function, time and space. So we have this leading order behavior. Times the Gaussian. And let me write it in terms of a scaling function of, so there's a natural scaling variable in the context of diffusive systems, x squared over t. Which I'll just call y. Okay. But we see that we have, so now we understand the general structure of corrections. Okay, we're going to have higher derivative corrections, which come with more and more powers of 1 over t, and which will come with their own scale. Second order higher derivative corrections, and so on. We have fluctuation corrections, which are suppressed by t to the d over 2. And will come with their own scaling functions. We have combinations of the two, higher derivative and higher fluctuation corrections. And okay, so the effective field theory is a double expansion in loops and in derivatives. And it gives us the general structure of observables at late times or low frequencies. But not only does it give us this general structure, it actually gives predictions for, it predicts these scaling functions. So these scaling functions are completely universal. Okay, this first one you know very well is just the Gaussian I wrote over there. Four. The coefficients in front of these scaling functions are not universal. They depend on things like diffusivities, which the effective doesn't predict. But once you know the coefficient, the entire functional form, the entire function is completely fixed. And you can compute the first few from the effective field theory. Maybe, let me just write one of them. And it has a form, it's going to be the same in any diffusive system. The exact form isn't really important, but I just want to illustrate that these things can be computed. They're really quantitative predictions from the effective field theory. And these predictions have been tested against numerics in diffusive spin chains, and there's really good agreement with numerics. So the point of this is mostly to tell you that these effective field theories do have a lot of predictive power. There's it's not microscopic, so we don't have access to there's a few unknown coefficients, but they make way more predictions than there are unknown parameters. Okay, they make whole functions worth of predictions, and you can test them against numerics. Okay, any questions about this? Yes. Yes, yeah, sorry. So that's right. So we said it's a kind of double expansion in derivatives and in loops. So F, let me call it Ln, is the L loop nth order in derivative correction to diffusion. Okay, and these come with prefactors. The prefactors are so here I didn't write the prefactor. The prefactors are not universal, but in some cases, for example, this one loop, the prefactor is just d prime squared. So if you measure the diffusion constant of your system at several temperatures, you would know d prime, and you would have a prediction for this correction. Yep. Right. Yeah. So these things have been tested in numerics, where there are situations where you measure leading order response as well as you can, get the diffusion constant, get its dependence on filling, and then you study other things like nonlinear response, corrections to linear response, and your hands are tied because let's say you measured diffusion as a function of filling. You have some curve for diffusion as a function of filling. This tells you what the cubic vertices are in the effective field theory, and now they're predictions with no more fitting parameters, right? For correct whole functions worth of predictions for nonlinear response. Nonlinear response depends on many coordinates, so it's really a lot of data. Correction to linear response, and yeah, you can. There are very few parameters, is what I'm saying. There's one parameter, and the prediction is there's an infinite number of predictions because you're predicting entire functions. So there's one parameter that you fit, the diffusion constant, and you can predict entire functions: linear response, nonlinear response. And there are other conceptual consequences of these functions that we'll come to in a bit. Okay, so now I'm going to move on to transport bounds. And so, okay, so there's several motivations for this. One motivation is that these effective, even just kind of theoretically, these effective field theories make a lot of predictions. They do have predictive power, but they do not predict things you might care about, the value of transport parameter of connectivities, diffusivities, and so on. They do not predict these things. So to actually get these objects, these parameters that enter the EFT, you would have to do microscopics. evaluate the Kubo formula or something like that. And this typically is hard, well, especially in the types of systems we care about that are strongly correlated. So given that it's difficult, it might be nice if there's some universal bounds on these objects. Okay, since we can't compute them, if there's just following from general principles, a universal bound that these objects must satisfy, that would be very useful. And this really, I think is kind of shares motivation with a lot of other work in the field of finding UV-IR constraints on emergence. Okay, where the hope is that knowing maybe a little bit about the microscopics, even though you can't actually compute things, helps constrain in some way, not evaluate, but at least constrain what can happen. Okay, and so there are many successful examples like Lieb-Schultz-Mattis, anomaly matching type arguments, Lieb-Robinson bounds, sum rules, and so on. These are situations where you can say something about emergence, you can constrain emergence, even though you can't actually compute things in a controlled way. So that's so even theoretically, it would be nice to have these things to constrain emergence. And an experimental motivation that has driven a lot of this work is hope. A possible hope that this could explain universal transport phenomena observed in strongly correlated systems, not by actually providing a mechanism, for what drives linear temperature resistivity, but just if you could prove, for example, that resistivity or some time scale is bounded by T, then you could argue that many strongly coupled systems that don't have small parameters in them are going to be close to the bound, are going to come close to saturating this bound. Okay, we saw with Debanjan how it's very mysterious how many systems, both strongly coupled and less strongly coupled, have Planckian physics. You could hope that this is explained by the fact that there's a universal bound and that many things are pushing against this bound. So this is the motivation for bounds on transport. Okay, so let me start with an example, not quite of a bound, but of similar ideas that have played an important role historically, namely the Mathieu-Ferrigo limit that Debanjan talked a little bit about yesterday, which is simply the idea that, so the statement that because we have limited power, we often use semi-classical techniques to study transports. Okay, and a semi-classical approach has limitations. So if you use Boltzmann semi-classical kinetic theory and compute mean free times of your particles, if the mean free time is shorter than the resolution of your particles, you probably shouldn't trust your results, right? So semi-classical approach to transport. So for particles, for the fermions near the Fermi surface, it will only make sense if the mean free path is large enough, is larger than their spatial resolution, the extent to which they're point-like. Okay, and inserting this in the Drude formula, will give us a limit on the conductivity for it to be describable by quasi-particle transport. This is the Drude formula for conductivity that we talked about with the Benjamin. So density is going to be kf to the d. M is going to be kf divided by vf. How? The mean free path is mean free time times vf, and so we land on e squared on this quantity, which better be larger than e squared af. So this is not really a bound because it assumes quasi-particle description. But what's surprising is that things actually happen around that value. It still tells us something interesting. If you look at the conductivity of metals, both good and bad, say DC resistivity divided by the Matyoff-Eragel value, as a function of temperature, at high temperatures. So extremely good metals like copper have, very small resistivities. But interestingly, many metals have slightly worse resistivities and seem to saturate at this Matyoff-Eragel value. And this saturation, I think, even in these less good but still decent metals is also not completely understood. And part of the interest in this bound is also in the fact that it's completely violated in many materials called bad metals. Like many of the cuprates, as we saw in the Banjan's talk. So this is kind of interesting. It's not an actual bound; it can be violated, but it's pointing at non-quasi-particle. It's suggesting strongly that there should be non-quasi-particle transports in bad metals. Okay, so it still has some interesting information, even though the assumptions are a bit too strong. Sorry? You could try to find a loophole, but it's going to be hard. So it's not necessarily saying the system is strongly coupled, but it's saying this system doesn't have a semi-classical description, right? You can't in this mean free path picture of quasi-particles, the mean free path of the quasi-particle. So it's very hard to justify in semi-classical picture. Yeah. Okay, so now let's try to lift this quasi-particle assumption and look for bounds on transports that apply in general. And there's been a lot of work, especially conjectures, on possible such bounds, such strong coupling bounds on transports. And the kind of intuition for why you might expect such a bound is that first, at weak coupling, with some work, you can compute a lot. You can compute a lot of transport parameters. And they all have a fairly simple coupling dependence. So at weak coupling, in a clean system, conductivities, diffusivities, all these things are extremely large and go like 1 over 2 to 2 scattering coupling squared. So these transport parameters are very large. Okay, it's very easy to conduct through a system that doesn't have many. So transport is very large, and you can make it smaller and smaller by cranking up coupling, by going to stronger and stronger coupling. Okay. Of course, at some point, this weak coupling prediction fails, and you shouldn't trust it. But at least it seems like you can make these parameters smaller and smaller. So they can be as large as they want, but it seems like you can also make them smaller and smaller. What has motivated a lot of the conjectured bounds on transport is many examples of solvable, strongly coupled quantum many-body systems. Where these transport parameters don't just keep on going down to 0, they have some finite value, some order 1 value. Order 1, I'll restore units in a bit, but not extremely small. And so these examples of strongly coupled systems come from holography and SYK-like models, for example. So these are very interesting points. They may or may not be generic, but they at least suggest that transport doesn't keep on, thermalization doesn't keep on happening faster and faster. There seems to be a limit, at least in the examples that we can study. It's just bounds on transport or thermalization that are close to being saturated at strong coupling. And that makes them particularly interesting because these bounds are most potent, are doing the most work in situations where you probably don't have analytic control. Okay, so there's several versions of these conjectured bounds. Let me go through them. Observables. The first, my favorite, is the Planckin conjecture on the equilibration time that Debanjan already mentioned. Okay, which is the statement that there's a quantum limit to how fast a many-body system can equilibrate. I mention it first because you could kind of think of it as a seed for other bounds, because in kinetic theory you often express transport parameters or diffusivities in terms of an equilibration time. But all the bounds are independent. So we'll talk more about this one in a bit. Another version of these bounds, these conjectured bounds, are bounds on diffusion. Which also involve this Planckian timescale and a velocity. And so the motivation for these bounds, or the maybe evidence, first came from high energy physics, from holographic models, the calculation of the shear viscosity in a holographic model. So we saw that continuous systems have conserved momentum. Momentum transport is characterized by shear viscosity, and the shear viscosity seemed to have an interesting behavior. So at weak coupling, maybe let me illustrate this with QCD. So QCD at high temperature becomes asymptotically free. And so the statement I made over there holds. Transport is very slow. Thermalization is very slow. Viscosities are very large. And whereas at very strong coupling, so we don't really have ways to study QCD analytically at strong coupling, but there are holographic models that look a lot like strongly coupled QCD. And experiments seem to agree that QCD at intermediate temperatures, which become strongly coupled, this ratio of shear viscosity to entropy is order 1. Okay, so it doesn't keep on going down as you crank up coupling. It's at some point it stops. And this led to the conjecture that 8 over S is bounded by 1. And there are H bars here, but I'm not going to put them. Now, this bound can be formulated as a diffusion bound, as we saw. Because we saw yesterday that shear momentum modes in a fluid diffuse, and the diffusion constant is set by the shear viscosity. Okay, let me just say it. So the diffusion constant of shear momentum modes that we studied yesterday was given by the shear viscosity divided by the momentum susceptibility. Okay, so a bound on viscosity will translate to a bound on diffusion, on at least this diffusivity. Now, for the relativistic QFTs that this applied to, the momentum susceptibility turns out to be fixed by symmetry, to be S times T. And so here we have our times C squared if I restore times speed of light. And so if I plug in this conjecture, we'll have a conjectured bound on the diffusivity, which looks like this. Okay, and this is a nice way to write it because viscosity, only is a reasonable object to consider when you have exact momentum conservation, or a good approximation, whereas diffusivities, as we've seen, are all over the place. And so if they're bounded, that would be good to know. And so this suggests a generalization where, hopefully in strongly correlated metals, it's not the speed of light that enters, but some other velocity, more relevant velocity. Perhaps the Fermi velocity. And what's appealing about this bound is that metals saturating such a bound with the Fermi velocity have T-linear resistivity. So the susceptibility of a metal is just factors of VF and KF, roughly. And diffusivity, let's say we're saturating the bound. So the diffusivity is VF squared over T. So these things simplify, and you can write it in terms of the effective mass and density, like in the Kubo formula. So going back to the Drude formula that the Debanjan wrote, this you would identify this as a kind of Planckian transport time. Okay, so this bound, if it were true, would be kind of doing the right thing. So there's no proof of this bound, but there has been progress on a related bound that actually goes in the other opposite direction, which I'll talk about in a bit. Yeah.
London also said yesterday there's many cases where transport is not set by diffusivity, but by compressibility.
Yes.
So would this bound not apply?
So, okay, this bound isn't proven, so it's unclear if it should apply. Yeah, so the systems you have in mind, I think, have constant diffusion constants at a very high T. So it looks like this bound would kind of apply, but trivially to those systems. Yes. Yeah. That's right. So here I'm kind of generalizing. So indeed, the motivation, maybe evidence for this bound comes from momentum diffusion in systems with momentum conservation. But we can hope, we can conjecture, you can generalize this conjecture to the thing on the top with some velocity. And yeah, here I'm exploring the possibility that this bound holds and maybe is saturated with the Fermi velocity in metals. Okay, so that's another example, and a final example of a bound on transport, a strong coupling bound on transport that has this flavor, is one that requires the most assumptions, but in exchange, it can be a sharp statement can be made, and it's the bound on the Lyapunov exponent. That arises in certain semi-classical systems. So this is so it requires the strongest assumption to define, but we'll be able to make a sharp statement. In this context is the out-of-time ordered correlator, which has no experimental relevance. But in certain systems, it has this interesting behavior, which is reminiscent of classical chaos, that it grows exponentially at early times. Okay, it's reminiscent of classical chaos because you can kind of think of this as a commutator squared, and it's telling you in the classical limit it would be a Poisson bracket squared, which tells you about sensitivity to initial conditions. So classically, the Lyapunov exponents are very well studied, and in certain semi-classical situations, in particular large N models, the out-of-time ordered correlator, the quantum out-of-time ordered correlator actually behaves in this way. And if you assume it behaves in this way, then you can actually show that this time scale, the Lyapunov, 1 over the Lyapunov rate, is bounded. Okay, and this really has the flavor of these other bounds because at weak coupling, this quantity is very large. It will go like 1 over coupling squared, you know, 1 or some power 1 over coupling. So it really has very similar features. It's telling you about thermodynamics, and it does seem to have a sharp bound. Okay, so this has kind of motivated, you know, further given hope for the possibility of bounds on actual transport. Yep.
About the
Yeah.
So you show that it kind of fits well with linear resistivity.
Yeah.
What happens with like a more sharper non-linear resistivity? Need some power lower than 1. Would this balance down, or does it somehow cancel with the effectiveness?
So you want something like this, maybe? Yeah. Well, actually, so let's see. Good. Would this defy this bound? So let's try to get the diffusion constant of your system. So chi is still a constant, and you're saying sigma goes like 1 over t to the 2/3. So d goes like 1 over t to the 2/3. So that at very low t, right, at very low t, it looks like it's fast. Indeed. So if you extract it, the actual time scale you get in this context is still t, right? It's true that yeah. So okay, I'd have to think about whether it is a.
There's always issues like the
Yeah.
effective mass.
Let me answer this question in the context of the Planckian bound, where I know the answer. Here I'm a little bit less sure if it would be considered a counterexample. Maybe Debanjan. Okay. Yeah, it's a good question. In the context of the Planckian bound, it's not a counterexample because of the renormalization. But here, yeah, here. But you could also ask, is the model that gives you this correct? And yeah, but that's a good point. Yes.
An early time expression? Or?
Yes, it's kind of it's an early-ish time expression. In fact, it's an expression that holds in a window that usually doesn't exist between the Planckian time and the Planckian time times 1 or log n. Okay, but in large N systems, you might have a window where you see this. Yes. So you know, hopefully we can prove bounds, and then they'll have to be satisfied in every system. But maybe you're asking, if one is saturated, do you expect others to be saturated? Yeah. So I mean, not in the sense, maybe not in the sense of exactly saturated, but definitely at strong coupling, you expect them all to be close to saturation. That's the expectation. Yes. Sorry.
In what sense does that window not exist?
Well, just in the sense that this window, sorry. N is the number of degrees of freedom per site, which might be 1 or 2, in which case there's no window. Okay, let me tell you a little bit about one direction which has seen some progress. It's not quite a strong coupling bound on transport, but it is a bound on transport, which flavor of these UVIR constraints. And it comes from constraints due to causality. Causality bound on diffusion. which applies to systems that have a kind of light cone. Okay, yes. No. Yeah, so proving this just comes from analyticity properties of this correlation function. It's very low tech, very simple. All the mileage is in the assumption that it behaves like this. So let's consider a system with a light cone, and with me a little bit why you would want to do that. So what I mean by that is that a system where operators commute exactly, exactly when they're too far apart, when they're space-like separated. Okay, so that if I have an operator here and an operator there, these two operators commute. So this thing, this type of but also in random unitary circuits where you have, kind of brick wall type. Let's say you have a brick wall type evolution, then you have a light cone, because you can't go faster than this velocity. But it applies approximately to local lattice models where this commutator is not zero, but it's very small, thanks to the Lieb-Robinson bounds. Okay, so it's not a crazy constraint to have. And what's interesting about this constraint is that it seems to be blatantly violated by diffusion, because diffusion spreads like this. So at very late times, diffusion is very slow, but at early times, it's faster than any light cone. Okay. Of course, that's not a contradiction because diffusion is never the microscopic, description of the system. It's emergent in any situation of interest. But it tells you that it can't emerge too soon. Otherwise, it would. The prediction, diffusion tells us there's big spectral weights everywhere here. This would violate causality if diffusion emerged too soon. Yeah, so let me write that's right. So this tells you that, whenever hydrodynamics does spying, that timescale should be later than when these two curves crossed. Okay. And so if you just equate these two things, you'll find that that timescale better not be too small, or diffusion constant better not be too big. So there's no violation of causality if the diffusivity is this. Okay. The squiggle. This inequality. Yeah. And I put the Lieb-Robinson velocity times the timescale at which diffusion emerges. Okay, so it's not a strong coupling bound in the sense that, even at weak coupling, both of these things are large. So actually, it's also relevant at weak coupling, right? Because systems take a long time to equilibrate, diffusivities are large. So it's not really a bound that's truly probing strong coupling physics, but it's still a non-trivial bound. And there are many refinements of this bound. Here, the way I presented it, it's but this has been made sharper in several contexts. You can also make it a little bit stronger. The Lieb-Robinson velocity is a bit of a loose bound. You can this a little bit stronger. And there's some references in the notes. Yes.
That's the time on the y-axis. That's where they cross.
So where they, right, it doesn't have to be where they cross, but it better be after, at least, you know.
I mean, just
Yeah.
diffusion doesn't apply below that time.
That's right. Diffusion doesn't apply before the time step. That's what I mean. Yeah.
Can you say what this VLR?
The Lieb-Robinson velocity. What it's related to? Yeah. So you know, it's related to properties of your lattice model. Okay. The other. It's a, that's right. It's a, there's a bandwidth. There's a J. Okay. I won't write the right formula, but you can look it up. Yeah. So it's, you know, it's related to properties of your lattice model. So you have a lattice model with bounded Hilbert space, and there's some, you know, yeah, it has some energy scales from hopping and so on. And
Fermions, is it related to V Fermi?
it's not. It bounds V Fermi.
1 over the reciprocal lattice. You know, so it's
Yeah, and it bounds most things. So it will bound V Fermi actually. So you might hope, yeah. So because of that, you might hope for something a little bit stronger, you know, and more relevant to, right. And there have been, you know, progress in this direction as well. Yes. Yes, and this is where we'll get to. I think that's a good way to think of it. So this question brings us to the Planckian bound. Yep.
I don't
Yeah.
Limit on D as opposed to just a limit on diffusion.
Yeah,
More like introduce a time scale below which you cannot use diffusion. Okay. So this way it's
you're happy with this? Yeah. Okay. So yeah, that was the question. Yeah, completely different physics. And no, but I actually agree with this. And in fact, that brings us to Planckian bound on thermalization. You could think of this already as indeed as a bound on the equilibration time, except it's still involving transport, which is highly non-trivial. I would like the, you know, what is it, right hand side of that thing to be simpler. Okay. So this equation has been proposed for a while, and you know, so there's several. So there's first a formal question, which is there any time scale, you know, for which this applies to? We saw already some counterexamples with the Benjamin that I'll talk about, depending on what time scale you use. So that's a kind of formal question. Is there, you know, can you define a natural notion of local equilibration where this bound applies? And then there's an experimental motivation, which is that bound experimentally relevant for that definition of local equilibration? Okay, and I'll show you that the answer is yes. There is such a bound. Unfortunately, it won't quite be the transport time you get from the DC connectivity that you know, de Banjan wanted. So you know, we don't get the bound we want, we get the bound we deserve, but it's still a time scale that will be relevant for transport for experiments. Okay. So right. So let's first think about how to define this time scale. So de Banjan already talked about in situations with quasi-particles, a good definition of this time scale is the time scale of inelastic scattering. Okay, you could add large angle scattering of particles. Okay, because you know, disorder can the elastic scattering of particles, even of otherwise free particles, and that is finite at zero temperature, violating any such bound. Okay, so so this seems like a good definition for quasi-particle systems. As de Banjan said, unfortunately it's hard to disentangle these two timescales. It's not like you have an experiment that measures elastic and another that measures inelastic. Okay, so that's a little bit unfortunate. And also it kind of relies on a quasi-particle description. So let's look for a more general definition of this timescale. Okay, so let me try to give a first non-quasi-particle definition. Which is to look for decay of stuff, of local operators, let's say. Okay, so I won't tell you what operator, but let's say you look for, you look at correlation functions of your local operators at finite temperature, and you might expect them to decay exponentially. And this would be a natural notion of local thermalization. And there are many models where this happens, where you can get these rates. And typically, they have the usual properties. At weak coupling, the rate is very, the time scale is very long, and at strong coupling, it seems to be Planckian bounded. But it's one issue with this definition is that it's hard to prove that things decay exponentially. And in fact, there are many models where nothing decays exponentially. So let me just give you one example to illustrate this point. You could do it in many models, but I'm just going to look at a transverse field Ising model. In the dimension of your choice, maybe let's just do 1D for simplicity. So I mentioned this as an example already yesterday. So this is a model that has almost no symmetry. There's no Z2 symmetry even, I broke it. It does have energy conservation though. So you expect energy to diffuse at finite temperature. So that if you look at the 2-point function of the energy density, okay, let me call this the Hamiltonian density. Its 2-point function should be diffusive. Okay, so it should decay like 1 over square root of t at late times. Okay, you have a little diffusive propagator. So obviously this operator doesn't decay exponentially because it's a conserved densities. That won't surprise anyone. So let's look for an operator that decays exponentially. Let's take, for example, a Pauli matrix. Okay, let's say sigma y. Let's look at the 2-point function of this Pauli matrix. Well, this 2-point function at late times also decays in a power law way with, in fact, the same power. It decays also diffusively in the exact same way. And the point is that there's no symmetry that forbids this operator from overlapping with energy density. Okay, maybe you could draw it as we have this operator that can decay into a diffuson. And therefore also feels this hydrodynamic tail. Okay, can someone think of another operator? Can we do better? Can we find exponential decay? Say again? Let's say a local operator. This would also apply to extended operators, but just for simplicity, let's say local operator. Sigma z, you could do sigma z. I'll do sigma z. Okay, I'll do sigma z in a bit. Let me do something else first. Yeah, thanks. No, it's a good example. It decays. Okay, I'll come to it. One thing you might say is, well, okay, this thing decayed polynomially because it overlapped with energy density. Let me just tune an operator that removes this overlap. Okay, let me consider. I'll call it sigma I tilde, which is sigma y minus some number, roughly this number times energy density. Okay, so this object by construction, I'm just canceling these two things. Okay, by construction, decays faster, but it turns out that it still decays polynomially, just with a slightly faster power. And the reason is that there's no symmetry that forbids it from overlapping with two diffusons, which still have long time correlations. Okay. So you can kind of, any microscopic operator you have, you can write down any EFT composite operator that it could decay into. In this case, it would be H squared, and that will give you the leading prediction. We can do it for sigma z. You mentioned sigma z. So this one flips sign under a symmetry that involves parity and spin flip. And so it turns out that actually the leading hydro operator it overlaps with is the derivative of H. And so you can check that this thing decays as dxh squared, which is 1 over square root t. 2 gradients gives you 1 over t. So it decays like 1 over t to the 3/2. And you can keep on doing this. Any operator you want, you just write down a hydro operator with the same symmetries, and that will tell you how it decays. Yes? Yeah, it's not clear that there is a regime. So there are models where this exists. I'm not saying it's a bad definition, but it won't be a universal definition. If you have a specific model in mind, it might be a good definition. And in fact, in metals, you could say the fermionic decay rate might be a good thing. That doesn't overlap with any hydro.
Expound and think of parallels just like a very, very short, a very, very long exponent, and it doesn't valid. So we don't really have to worry about these examples.
That's right. I'm just saying, so we'd like to prove the bound. We haven't proven the bound yet. I'm not saying these are counterexamples to the bound. I'm trying to define the equilibration time. You might have hoped for a definition that says, oh, it's the slow of a non-hydrodynamic field, of a non-hydrodynamic operator, okay? But all non-hydrodynamics in certain examples. So that's all. Yeah, it's not violating anything. It's just making the definition a little bit more subtle. But this brings us to another definition that will be more robust and more universal. Definition number 2, which is to, here we're suffering from this hydrodynamic pollution of all correlation functions. But instead of suffering from this, we can use our knowledge of hydrodynamics and the fact that it always emerges to define the timescale as the timescale of emergence of hydrodynamics for diffusion. Okay, so, and you could look at any observable you like. Let's stick to this density 2-point function. So it's going to have some behavior, at early times that's not universal. But at late times, you expect diffusion to emerge, and you expect it to approach a diffusive behavior. Okay, so at least qualitatively, this is a notion of equilibration that makes a lot of sense. I mean, it's really what we mean by local equilibration, right? Hydrodynamics is what emerges after local equilibration. It's then hydrodynamics that controls global equilibration. And you can also make this more precise. Talked about this in his poster. You can look at it. You can put some epsilons and deltas to make this a little bit more precise. I won't do this here. To get a precise notion of the equilibration time. Okay, and this definition, you can apply it to any system, any local system. It has exactly the properties that we have been talking about. At weak coupling, hydro takes a long time to emerge because you need to wait for all non-conserved quantities, quasi-particles and so on, non-conserved excitations to decay. So tau-ec is very large at weak coupling. And you can ask, can it emerge arbitrarily early? can you crank up coupling and make the system thermalize faster and faster, make hydrodynamics or diffusion emerge faster and faster? The answer is no. In fact, hydrodynamic EFTs themselves tell you that they cannot hold at arbitrary early times because they have all these corrections. Okay, we saw that observables, any observables at late times or at small frequencies have some leading behavior, diffusion or Navier-Stokes, depending on what your hydrodynamic theory is. But it's never the exact description. It's always emergent, so it has intermediate time corrections. There are many of them. We talked about one of them. That was this one loop effect, but there are many such corrections. Okay, and if I go, so these are small at late times, but if I go back to earlier times, they become large and they give a completely non-diffusive behavior. At some point, this thing breaks down and it tells you that it's breaking down. It's giving you a time scale at which it is not valid. Okay, these corrections that we talked about in the beginning of this lecture must die off